Okay, we know uniformly continuity is a stronger condition to continuity, just the continuity. Okay, so but we'll prove that any continuous map defined on a sequentially compact set is uniformly continuous. So this is our main theorem. If A is sequentially compact and the F is continuous defined on A, then F is uniformly continuous on A. Okay. Now we prove this theorem to demonstrate an application of the previous proposition proof. So we according to this proposition, it's sufficient to see that for any two sequences that become closer and closer, the image of the sequence under F are also become closer and closer. Therefore, let xk, yk be sequence in A, and the distance and the difference from this sequence converge to 0. Okay. We will show that fxk minus fyk, the norm of fk minus fyk, is also goes to 0. Okay. So if this is not true, we argue by contradiction. If not, so if this is not true, then this is a sequence of real number which does not go to 0. Which does not go to 0. So since this sequence of real number is not converged to 0, then there is a epsilon positive and a subsequence. And the subsequence xki and yki, such that the distance from fxki to fyki is always not less than epsilon. Okay. Of course, these two subsequences are all contained in the set A. So A is sequentially compact. Therefore, A is bounded and closed. Okay. So xki will have a convergent subsequence. Since A is bounded, the sequence xki and yki also bounded. Are also bounded. Therefore, xki will have a convergent subsequence. Okay, xki and yki are bounded. Therefore, xki has a convergent subsequence. We let xkij, the index is j here, be a convergent subsequence of xki. We might assume xkij converge to some point, say A. But xkij is a sequence in A, therefore this point A will belongs to the set A. But we know that xk minus yk converge to 0. Okay, so and xkij converges to a. Therefore, we must have ykij also converge to a. Okay. It is easy. Yki minus a will not greater than by the triangle inequality Yki minus xkij plus xkij minus a. Now this part converges to 0, and this part is a subsequence of the norm of xk minus yk. Therefore, also goes to 0. So this implies that this goes to 0, and this proves our claim that ykij converges to a. So by the continuity of f, we have fxkij goes to fa, and fykij also goes to fa because ykij converges to a. So fxkij minus fykij goes to 0. Or if you don't believe, you can use the triangle inequality again. Now both these two terms on the right hand side goes to 0. Therefore, eventually this goes to 0. So this means that this goes to 0. The left hand side goes to 0. But by our choice of the sequence xk, yk, we always have the fxkij minus fkyKij has a positive lower bound, epsilon. So any subsequence of the norm of fxki minus fyki could not go to 0. But now we get a subsequence of that sequence which goes to 0. That is this right hand side here. So this is a contradiction. This contradiction tells us that f must be uniformly continuous. Okay. Okay. Now we will consider another property of continuous map. This is related to the intermediate value property of a continuous function. And for this property, we need to impose some special restriction on the domain of definition, which is pathwise connectedness. Okay, so this is our next section. Pathwise connectedness. And the property we will investigate to the function is intermediate value properties. Okay. So first we will fix some notation. Suppose A and B are 2 points in Rn, then we use this notation AB like an interval, but the endpoint of this interval is not real numbers, it's point in Rn. Okay, what this means? This means the segment which endpoints A and B, or 1 minus T A plus T B. Here T runs from 1, 0, 1 interval. Okay, so here is the point A, and here is the point B. When the T is 0, 1 minus TA plus TB is exactly A. As T increases from 0 to 1, our point 1 minus TA plus TB will go from A to B. So this is the segment between these 2 points. We call this a segment which endpoint A and B. segment which endpoint A and B. Okay, so this is the our first definition. And using the segment, we can define convexity, convex set. A subset S in Rn is called convex. If whenever AB are for any 2 points from this set S, the segment between these 2 points belongs contained in S. Okay, so this is quite intuitive. We draw a picture to have a look. So this set is convex because given any 2 points, the segment between them contained in S. But this set is not convex because this point and this point, we consider the segment joining these 2 points. We see that this part of the segment is not contained in S. Okay, so the convexity is quite easy. So there are many important convex sets. For example, any ball centered at any point and with any radius is convex. Okay, remember this ball is the point x in Rn. The distance from x to the center less than r. So this is ball. These balls are always convex. How to prove this? The proof is easy. For x and y belongs to this ball, we need to prove that the segment which endpoints x and y are contained in this ball. Therefore, to prove this, we know any point in this segment can be written as 1 minus tx plus ty for t belongs to the interval 0, 1. Okay, so we need to prove that any point of this form belongs to this ball. Therefore, we need to estimate the distance from this point to the center of the ball. So we estimate it as follows: 1 minus tx plus ty. This is the point on the segment. The distance from this point to the center of the ball, which can be writing in this way: 1 minus t x minus a plus t y minus a. Okay, we split the coefficient of a, that is 1, to be 1 minus t plus t. Therefore, we have this this expression. So we apply the triangle inequality. The right hand side will not greater than the absolute value of 1 minus t under the norm of x minus a plus the absolute value of t under the norm of y minus a. But t is taken from the interval 0, 1. So 1 minus t and t are all positive. Therefore, the absolute value is not necessary. So, but on the other hand, the norm of x minus a and the y minus a are all less than r. So the right hand side will less than 1 minus t r plus t r, which is exactly r. This proves that any point in the segment belongs to the ball. So balls are convex. Okay. So geometrically, any 2 points in the ball, the segment always contained in the point in the ball. Okay. So this is a simple example.